Before we can discuss the relationship involving object distance, image distance, focal length, etc., we need to follow certain sign convention. If this is a pole and mirror can be concave or convex, then reflecting side we are assuming is on the left side. So rays will come from the left, this will be the reflecting side, whether it's concave mirror or convex mirror. Right side will be positive, left side will be negative, upward will be positive, downward will be negative. So if this is reflecting side, then obviously object is on the left side. That means object distance will be considered as negative. In case of concave mirror, parallel rays meet at some point here, so that means focal length will be negative. But in case of a convex mirror, they appear to be meeting somewhere here, which is the right side. The focal length will be positive. If F is positive, R is positive. If F is negative, R is negative. R and F are on the same side, right? So if one is positive, other has to be positive. So it's a very simple sign convention, and it is useful for image also. I mean image, not just which side, but also the size of the image. That's why that up plus down minus thing comes into picture. If image is, let's say object is up but image is down, then image size is considered to be negative. So that's how up and down sign convention is important. Whatever mathematics we'll be doing will be valid for paraxial rays. Paraxial means rays that are close to the principal axis. The pronunciation of paraxial somewhat rhymes with parallel, but actually parallel has nothing to do with paraxial. Paraxial has nothing to do with parallel. Paraxial only means close to the principal axis. That's a different thing, that parallel rays which are paraxial also, they meet at the focus, or they appear to be meeting at focus. We are now going to do mathematics. We will do it for concave mirror, but it works for convex mirror also. Also in the figure, it may look like that object is at one particular location, but again, the result works in all cases, all locations of the object. Construct a normal. Now, this ray, angle I will be equal to angle R. Another ray you can take absolutely straight. Will go hit here, bounce back. So these two rays will meet at this point. That's where we are going to have image. This is pole, and that point, call it whatever you like, maybe Q. Now we need three angles, maybe alpha, beta, gamma. In fact, we begin with angles, and then this is angle of incidence, this is angle of reflection. Both can be taken as II or IR, where I equal to R. Now this is the exterior angle, so beta would be equal to alpha plus I, and gamma is also exterior angle, which will be beta plus R. R is I, and beta is alpha plus I. So gamma is alpha plus 2I. We actually don't want I. I should not come. Now beta is in terms of I, gamma is in terms of I. No problem in eliminating I. Multiplying this equation by 2, and now this minus this. So we have 2 beta minus gamma equal to alpha, or 2 beta equal to alpha plus gamma. Now you will see the importance of the word paraxial. These angles are actually very small, what may look like big. We are considering rays which are close. These angles are small. So while this is the real center, so angle equal to arc upon radius will be best for this. This is not the real center. So is this not the real center. But we will still apply angle equal to arc upon radius, because we are talking about paraxial rays. So that approximation we are making, arc PQ upon radius CP. For alpha it will be arc PQ upon radius OP. This is approximated. Gamma arc PQ radius IP, also approximated. Right side is approximated, left side is accurate. Putting approximation sign, cancelling PQ. 2 by CP equal to 1 upon OP plus 1 upon IP. Now in this particular drawing, now note that CP, OP and IP are lengths, actual lengths, positive, they are all positive. But image distance, object distance can be positive or negative. For object distance we use U, for image distance we use V, focal length F. They all can be positive, negative. But actual measured lengths like CP, which are written from geometry, they can never be negative. So if I want to write CP as capital R, then I must keep in mind that R is negative here. If R is negative but CP is positive, then CP should be minus R. Likewise, OP is length, it's positive, but object distance is negative. OP is positive, U is negative, so minus U is positive. Then IP, in this particular drawing, image has to be on the left side. But IP is the actual length, it is positive. It is a geometrical length, it's positive. But if I put V, then V is certainly negative. But minus V is positive. Now you get this result. 2 by R equal to 1 upon U plus 1 upon V. Till this point, f is not there. In fact, f is defined in a particular way. When we say that rays coming from infinity, they meet at a point which is focus, then we are able to get focal length very quickly from this. Rays infinity, u is infinity. Rays parallel means u is infinity. Then V is equal to f. So 2 by r equal to 1 upon infinity plus 1 upon f. That's the proof for f equal to r by 2. F equal to r by 2. Any questions up to this point? Let me know. Magnification discussion cannot be done from this drawing. In this drawing, point object was taken. So for magnification discussion, we will have to redraw. Again, one particular situation we are taking, but the result works in all cases. Let's say this is C, this is the object. We take one ray which is parallel, it goes via F. Other ray we can take via C, it will just bounce back. Intersection is here, and the image of this point will be here. That can be easily checked. 2 points are enough to construct a straight line, or straight line segment rather. And we are done. It's inverted in this case. Let's say this is AB. Image of A is A dash, image of B is B dash. We will look at two triangles. I have just taken one more ray. Angle I will be angle R. This is a normal. It has to go through this. No other choice. All rays you take from B will have to go through B dash after reflection. Now these two triangles are going to be very useful. 90, 90, angle same, I equal to R. A is similarity, angle similarity. Angle I equal to angle R, 90, 90. These are similar triangles. We are talking about geometry. So these are the lengths, positive. AB upon A dash B dash. Let's say that is P. That is equal to distance PA divided by distance PA dash. All positive everywhere. PA. Now U, if I want to use, then I know U is negative, but PA is positive, so I must use minus V. Then PA dash, V, but I know V is negative, but PA dash is positive, so I must use minus V. Let me write A dash B dash up, AB down. that is V by U. For this concept of magnification, we just don't want the size comparison, we also want inverted or non-inverted type of situation. So we define capital O as object size with sign, and capital I image size with sign. Following that convention, up is positive, down is negative. O is with sign, positive, negative. I is with sign, positive, negative. For this particular situation, O is, object is up, so O is plus positive number. AB is positive. These are all lengths, geometrical lengths. So in place of AB, I can just write O. But A dash B dash is a geometrical length, while I is, in this drawing, I is negative. So I must put minus I for A dash B dash. Only then can this be a positive number. And magnification is defined as I by O. That's the definition of magnification. Magnification will tell you not only about the size comparison, but also about inverted or not. So I by O is minus V by U, or M is minus V by U. Now we have done the mathematics involving the curve mirrors. Any questions? Let me know. This result, which was 1 upon U plus 1 upon V equal to 2 upon R, can be written as 1 upon U plus 1 upon V equal to 1 upon F. That's normally what you memorize, but you memorize this also, F equal to R by 2, and this also. These results work for the sign convention that we have followed. That sign convention is called Cartesian sign convention. There used to be another sign convention popular several years ago, based on real and virtual. It was more difficult, but it would work also. But then the results could be different. These results have been derived following the Cartesian sign convention: right positive, left negative, up positive, down negative. This is a summary to help in ray diagram. Parallel to principal axis reflects 2f. 2f reflects parallel to principal axis. This one. Dash 2. The one that goes through C will just bounce back. Image on the left side, it has to be real. While often we don't show more rays, but any other ray you choose must follow its path through this. Now, answer this question, which is not correct. 1, 2, 3. Yes, it has to be 3. Ray going through C must bounce back, but it seems to be going somewhere else. It should have come back. 3 is not correct. And now, try to answer this question. Well, U is negative, left side, S is negative. When one negative is subtracted from another negative, how can we say the result will always be negative or always be positive? And what if V becomes negative? Image is on the right side. right side where no rays can exist. V can be negative or positive. If V is positive, image is on the right side, it is virtual. If V is negative, image is on the left side, it is real. Any questions? Let me know. Now try this one. You have the explanation in front of you. If you have any questions, let me know. We have already done this derivation. So this slide can be skipped. This application should be done. A candle is placed 6 cm in front of a concave mirror with focal length f equal to 2 cm. Determine the image location. Try to do it quickly. It's formula based. Your answer is not very clear. 3 centimeters means what? So the answer is 3 centimeters in front of the mirror. Any questions here? If you have, let me know. And now answer this. Compared to the candle, the image will be larger, smaller, same size. Try this. What direction will the image arrow point? Up or down? Okay. Any questions regarding this? Let me know. It helps to remember some standard cases which are for real object. The way we did the derivation, that was this case, which was beyond C, and because we did the derivation that way, perhaps you may remember it more easily. We have in this case small image, and it is inverted, and it is real, of course. Then if the object is very close, this situation came up somewhere earlier. In that case, in fact this is the only case when the image is virtual on the right side. And not only that, it's the only case when the image is upright. Otherwise, in all cases, other cases, image is opposite. So this is inside F. Image is straight, virtual, big. Now between these two situations, between F and C, real image, big, inverted. So it helps if you have these three cases in your mind. Here when we say through F, through center, that's not going to be possible literally. So towards center, towards F, that sounds better. Now always true means that's the only case. No three cases here, only one case. For real object. So if the object is real, you will have virtual image only, it will be upright only, it will be smaller in all cases. Whether you keep object closer, farther. So what's the answer to that question? A candle is placed 6 cm in front of a convex mirror with focal length f equal to 3 cm. Determine the image location. Two centimeter to the right or left? Okay, plus 2 means to the right. Convex mirror is a reduced image case, so 1/3 should be fine. It is upright case, so it should be plus 1/3. And I hope you understand that observer is here. Observer is watching from left side. Observer is not on the other side. Whether rays go to the right side or not, they won't be going. They must reach the eyes. Otherwise, how can you see something? And right side, no rays are there. So eye will not get anything on the right side. Observer is on the left side. If the candle is 9 centimeter tall, how tall does the image of the candle appear to be? Any problem with that question? 9 centimeter tall object, magnification is 1 by 3. So image size should be how much? Three centimeters. Where should you place an object in front of a convex mirror to produce a real image? 4 options. We are talking about placing the object. It has to be a real thing. If the object is real, convex mirror, you can never get real image. Both, you cannot. Suppose we are talking about concave mirrors. Which graph you think is correct? U versus V versus U. Concave mirror. You know that when U is small, it's a case of virtual image. And you also know that it's a non-linear relationship. Reciprocal relationship. How can it be linear relationship? C is out. Now all the three have reversals. Other options all have reversals, time change. And in all of them, it is first minus, V minus, then V plus, V minus, then V plus, V minus, then V plus. When object is at infinity, rays go to the focus. So from principle of reversibility, if you keep something at focus, then rays should go to infinity. So how come if U is 0, V is becoming infinity, minus side of course. When U is becoming F, then V should be infinity. And actually the reversal takes place at focus. On the right side of focus, you have virtual image. Left side of focus, you have real image. This reversal happens at focus and happens in a big way. Look at this, infinity, infinity. But this is infinity, but this is not. And moreover, this is a big problem. At U equal to 0, how is V becoming infinity? Of course, minus side. A or D? I think I would leave it as an assignment, but you have to give some explanation, whichever option you choose. So that's your assignment question. We stop now.